Okay, so the plate boundaries are either going apart, together, or sliding side by side. We're going to go through the different plate boundaries in a little bit more detail now. The first one here is a divergent plate boundary. The plates are moving apart. Right at the plate boundary, the lithosphere is pretty thin, and then it thickens away from the plate boundary. This is a mid-ocean ridge. It's also called a spreading center or the spreading boundary. A convergent plate boundary is where the plates are moving together. Uh, Plates are consumed or recycled back down into the mantle at a subduction zone. The plate is subducting. This is called a convergent plate boundary, a subduction zone. We may just call them the trench. And then the last one is a transform plate boundary. And this is where two plates, instead of going apart or together, they're sliding side by side. Woo-woo. So there's not going to be plate material consumed like a convergent plate boundary, and it's not going to be made like a divergent plate boundary. So there's not going to be any volcanism, but there are earthquakes. So this is a transform boundary or a transform fault. All right, let's talk in detail now about that divergent plate boundary. The plates are moving apart. As they separate, then there's an upwelling of magma from the asthenosphere that comes up into that giant crack on the ocean floor. The melting occurs because of decompression. So the asthenosphere, remember, it's a solid, but it flows. So how are we getting liquid out of there? As the plates move apart, pressure comes off of the asthenosphere. That decompression promotes melting. So melting occurs as the pressure comes off and melt comes up into the gap that's made as the plates move apart. All of the material that comes up is from the mantle. So it has magnesium, iron, and they're silicates, the minerals that form, and it makes up the rock type basalt at the surface and then gabbro down below. So here is the stages of rifting. In the early stages, there's those faults like we saw at the edge of the passive margin. So eventually, as this ocean basin continues to separate, uh, ocean or seawater is going to fill in this space on either side. Then here on plate A and here on plate B, underneath what's going to be probably a cover of terrigenous sediment, are these little fault blocks. So that's what's showing here and what we saw earlier at the passive margin. So over time it would widen and water would come in. This is the beginnings of something like the Red Sea, early stages of the formation of an ocean basin. Over time, then it's going to continue to spread. These gray rocks were at the one time together at the mid-ocean ridge. Time two, now they've moved apart. We have those yellow rocks coming in between, just different colors to show stages in the formation of the ocean basin. The crust is thin there. It's oceanic crust now. Eventually, then we're going to get a wider ocean basin. We have a central raised ridge here. The edges of the ocean basin are the oldest, so over by the coast of North Carolina and over here by the continent of Africa, that's the oldest oceanic crust. The youngest is being formed here in the middle. So here's the example of the Atlantic Ocean. Then we flood that with water. Here's the mid-ocean ridge. In the South Atlantic, then it's moving apart 1.7 centimeters per year. There are these big fracture zones that offset the ridge. There are seamounts, these little old dormant volcanoes. Perhaps they're sitting on the seafloor. The edge of South America, the continent here, then is a passive margin, has a really wide continental shelf. Let's see what else. There is a hot spot track over here. This is tracking a hot spot, kind of like Hawaii, right? Along here. Here's a zoom in then on the mechanisms and the magma chamber here. So Here's a magma chamber, the zone of partial melting. Again, that is the decompression melting. As a weight comes off the asthenosphere, it starts to melt, and it's going to be less dense, that liquid is, than the surrounding rock. So it's going to rise up. Crystal mush means that it isn't totally liquid. There's some crystals in there. And then that magma is going to squeeze up through cracks within these little faults at the top of the mid-ocean ridge. Sediment. So there's thin layer of sediment on top of those basalts. The first layer, this light gray, is labeled pillow basalt. We'll see a little bit about that in a minute. So pillow basalts, and then lots and lots of basaltic dikes. Those are thin intrusions of basalt. And then below that, this lighter gray is called a gabbro. Gabbro is the same chemical makeup as a basalt. It just has bigger crystals in it. When I say bigger, we can see them. Bigger crystals, and those big crystals tell us that it cooled slower underground. So pillow basalts at the surface, followed by the dikes of magma, just intrusions of lots and lots and lots of basalt, and then below that, the gabbros, the crystalline, same chemistry as basalt, bigger crystals because it cooled underground, gabbro. All right, so let me, this is what a pillow basalt looks like, kind of lumps and bumps of bulbous pieces, blobs of basalt. I'm going to see if I can get this little video to show. We'll just watch a second of it. These people are scuba diving, so you can hear them breathing over the sound of the lava. Here it comes. Now we're out on the edge of Hawaii. Magma's dripping down into the ocean. Bobbing along in a boat. There we go, that's an action. There we go. Pillow basalts. Okay, so you can, this lasts a couple of minutes, but it forms a crust, and it breaks that crust, another blob of basalt comes out, and another one comes out, and that forms the top of the oceanic crust. We'll stop this and escape. Go back to our lecture. Here we are. Okay. Pillow basalts. The mid-ocean ridges, like I said, are volcanoes, and they are spewing out this smoke. It's called a black smoker. The black smoke is really hot water with dissolved minerals in it. So it's not like it's on fire. It's minerals dissolved in the really hot seawater. These organisms, different weird worms and shrimp, are thermophiles. They love living in this really hot water here. So the let's see if we can get this video to work. Yep.
Looks like maybe 12.
We have to be careful because we can melt things on
Yes, you can.
Right. Let's get some overhangs
Wow.
here.
That's magnificent.
Awesome!
All right, guys, how's worth the wait? Yes.
So this is a black smoker.
There it
All of the
is.
smoke coming
Wow.
out.
iconic structure of oceanography.
Iconic structure
Looks
of
like a little
oceanography.
beehive up there,
It
huh?
does, doesn't it?
It is a beehive.
Wow.
How long have we known about when was
Yep.
the first vent discovered?
The first vents were discovered in '77. The first
black smokers.
smokers in '82. That crab on the
Oh, yeah,
right
look at that.
may be Predator.
It's pretty cool,
Okay,
right?
I'm going to stop
Cyanogrea.
this, but take a minute if you will. Wait, can I stop it?
And those look just like Galateids,
Yeah.
but maybe.
Stopping. Take a minute, if you will, to look through those videos. All right. Black smokers. The oceanic crust, the age of it, is a neat look at ages. So in the color here, 0 is red, and then it goes through to these purples. So blue is really old crust, purple is very old, and green's like middle-aged crust. So looking at our ocean basins, where they're bright red, that is new today, right? Age 0, volcanoes are pumping out magma, basalt is forming new oceanic crust right there today. Then as it spreads away from the ridge, you get older and older and older to the oldest crusts on the edges. So for the mid-Atlantic ridge, the blues here right up next to Africa and right up here next to the east coast of North America. The lithosphere thickens over time. So here is the material right at the ridge. It's continuing to pump out. As it cools down away from the ridge, it's going to thicken and the density increases and it sinks down into the asthenosphere.